Okay, so what we're going to look at in this video is an analysis of wave interference, and we're going to do this analysis using something called path differences. So what we're going to look at first is what creates a stationary interference pattern. So what I've got is I got 2-point sources set up here. They are a given distance apart, and I'm going to start the waves, and we'll see that they propagate. Now in this, a green might mean a crest, red would be a trough, green would be a crest. So it's going to, and I think if I go to 3D view, I can actually show you that. So here we go. I'll start it again. So the green is a crest and the red is a trough. Okay. So what you'll see emerge is this very defined interference pattern. Okay. And you'll notice here that you get areas where it always seems that there's no waves, and then areas where there's lots of waves. Lots of waves, no waves. So in terms of interference, last year we looked at standing waves and we saw that there were nodes and antinodes. What you'll notice here is that the areas where there's no wave action in these lines right here are called nodal lines. Now they come about because if you stop this here, you'll see they come about, these dark banded nodal lines where there's no wave amplitude whatsoever, and then these bright antinode lines where there's maximum amplitude or constructive interference. The reason for that is that you can see that in between the point right here, you've got a trough and a crest meeting. And if a trough and a crest meet, you get destructive interference. And for that reason, you get destructive interference. But what's interesting is that there's very specific regions where a crest and a trough always meet, and you get these dark banded lines. And to create a stationary interference pattern like this that you see here, the two sources must be a single frequency, meaning both producing the same frequency. They can't change. If one starts changing, this you'll notice a change in the so here's 2 source 1 frequency. If I go 2 source 2 frequencies, so now they're different frequencies, you'll notice that there's a shifting of the nodal lines. So if I go back 2 source 1 frequency like so, you'll see that whenever I shift the frequency, the position of that nodal line shifts. So if you want a stationary interference pattern, you must have a single source frequency that's not changing. Constant separation. You can't move the distance between the sources. So if I move them closer, you'll notice that the position of those nodal lines gets different. Now there's less nodal lines, and very defined in fact. Now there's only 4 of them, and they've changed position. And so if I put them even closer, we'll end up with just 2. So 2 areas where there's completely destructive interference, and then more areas where there's very bright constructive interference where crests are meeting crests and troughs are meeting troughs. If I move it apart, you'll notice that again, as I get further apart, you will get more and more nodal lines, and the nodal lines will shift. If I get too far apart, after a little while, if I really separate them by a lot, what you'll notice is I'll clear these waves and have them emanate out. If I get too far apart, you may not even end up with nodal lines, and it'll just look like 2 independent sources. Now here you're getting lots of nodes. It's pretty weird. And in the middle you're getting this massive antinode happening right here. So, and the other thing you can't do is you can't change the phase. So they have to stay in phase, meaning that they're both bobbing up and down at the same rate. And if they were opposite, then you would do, it would also change it. I'm not sure I can change that in here, the phase, but if the phases stay the same, then you'll get a straight interference pattern like this that's unchanging. So again, it comes about because you've got crests and troughs meeting, and you get these things called nodal lines and antinode lines. So I'm going to turn this off, and then we're going to look at the situation about where these things happen. So take out your sheet and look at the analysis for this. What you're going to notice is what I've got here are crests and troughs. So we're going to represent the solid line as the crests and the dashed lines as the troughs. So we've got 2 sources that are vibrating, They are a very specific distance. We can calculate that distance, or measure it, sorry. We can measure that distance, d. And they're producing waves. These waves are going to be in phase and all those things I just mentioned a second ago. So in order to get a stationary interference pattern, you need the condition that they are single source frequency, they are constant separation, so unchanging. We don't want them changing. If they change, the nodal lines will change. That's the D value. And a constant phase, meaning don't change the phase. So the phase would be, one bobbing up, one bobbing down, and then you switch it to both bobbing up, both bobbing down. You can't change that situation. So at this point, we're just going to talk about a couple other things. This thing here is a right angle. So this dashed line that I've drawn here is the right bisector. Okay, so we'll see what that's about in just a minute. And what we're going to look at now is all the situations where crests meet troughs. So when we look at our sheet here, wherever a solid line meets a dashed line, that is going to be a position where a crest is meeting a trough. And if you notice this, what you'll see is that we're going to end up with, and there's actually other spots here. There's also one here, 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 and here. And on this side, there's also here and here. And you can see just like this. So what we'll notice is that these are what are called nodal lines. These are where all the nodes take place. So I start from here, and if I draw lines, that would be a nodal line n equal to 1. Is the second nodal line and the third nodal line. So those are those dark lines that you saw on the applet. Over here, it's symmetric on both sides. So this is n equal to 1, n equal to 2, and again, n equal to 3. It's symmetric, so we don't have to worry about that. Okay. One wavelength is defined as the distance between a crest and a crest, or a trough and a trough. So that distance from there to there is literally one wavelength. Okay, so we can see that. The next thing, maximums. Well, maximums occur whenever a crest and a crest meet and a trough meet. So don't draw this in, but I just want to give you an idea of what that would look like. If the nodes are here, the nodal lines, here's a crest and a crest, a trough and a trough, a crest and a crest, a trough and a trough, a crest and a crest, and you get the idea that this is going to be what we call a, well, you can't see that. This is what we're going to call a maximum. Okay, we're not looking at that yet. Nodal lines, these here, are called minimums, right? Because that's where you're getting destructive interference, and maximums are constructive interference. So that's the big difference between the two of them. So and there's lots of maximums. So this is constructive, and the other one is destructive interference of the waves. Right up the middle is the 0th order maximum. Okay, so we can see that right up the middle here, this is our 0 ordereth maximum. That's what we call it. 0th order maximum. And then there's a 1st order maximum, 2nd order maximum, so on and so forth. What we're focusing on for this is our destructive. So we're focusing on those darker lines, the n equals 1, the n equals 2, and the n equals 3. Now, of course, there's going to be more or less of these nodes depending on the frequency and the separation, as we saw in the applet just a few minutes ago. Okay, in order to get destructive interference, so we'll just write this down so you have in your notes, destructive interference. You must have what we call a nodal line. This is what we call a nodal line. You must have a crest meet a trough. And that we've already drawn in. Okay. In order for destructive interference to happen, where a crest meets a trough, what this means is that the waves, and this is the big point of today, the waves must be out of phase by a half a wavelength. It must be out of phase by half a wavelength, meaning a crest would lag behind a trough by 1/2 of a wavelength, or sorry, a crest and a crest, if one lags behind by half a wavelength, it then means that you're going to have a situation where a crest and a trough will meet. So how does this happen? This happens, they become out of phase, because we can clearly see that there's nodal lines, so they're definitely out of phase by that half a wavelength. They become out of phase because one wave must travel further than the other. And now you're thinking, how does that matter? Well, what we're going to call this, and I'll explain that in just one second, we're going to call this the path difference. Path difference. And it's the difference in the distance the waves travel. Okay, so it's a distance the waves travel. It's called the path difference. So what I'm going to do is I'll show you this. Up here on the first nodal line, okay, what I'm going to do is I'm going to draw a point, any point on this line, and just call it P. I'll just grab this point right here, and I'll call that point P. So at this point P, what we have is the situation where I'm going to draw a line from here to here, and I'm going to draw a line from here to here like this, and we know that this wave has to travel this far, and this wave is going to travel this far. And what we're saying is that in order for this to be a node, there has to be exactly 1/2 of a wavelength difference in that length. So you can clearly see that this one traveled further than this one. If I pick another spot, let's say P over here, that's P3, because we're on the third nodal line. This wave has to travel that far, and this wave has to travel that far. Well, the difference between this length and this length will be 1/2, or it'll actually not be 1/2 of a wavelength, it'll be out of phase by about 1.5 wavelengths. So we'll see that in just a second. So the path difference for the first one, we're saying that is going to be exactly 1/2 of a wavelength out of phase. So it looks like this. For the first nodal line, what we're looking at is that the P1, S1, so that's the distance from P1 to S1, minus the distance from P1 to S2, which is source 2, must equal lambda over 2, 1/2 of a wavelength. For the second nodal line, they're going to be out of phase by P2 S1 minus P2, so 0.2. S2 would be, we have to add 1 to that, so that's 3 lambda over 2. This continues, so we can see for the third one, it would be 3/2 of a wavelength. We'd go another half, so it's actually going to be out of phase by 1 wavelength in total, and that would also do it. So what we're going to look at next is that in general, here's what the equation looks like. Pn S1 minus Pn S2, so that's the n is the nodal number, so 1, 2, 3, 4, 5, or whatever number you get to, is equal to n minus 1/2 times the wavelength, where n is the nodal number. So for the third, it'd be 3 minus 1/2, which is 2 minus 1/2. Sorry, 3 minus 1/2, which is 2.5 wavelengths. So it would be 2.5 wavelengths out of phase. So that means that this one here would be 2.5 wavelengths behind from the other one. So we can actually measure this to check. I mean, just do a quick little measurement to see if this even makes sense at all. If we look at P1, we said it should be out of phase by 1/2 a wavelength. Well, what is the distance from P1 to S1? We can literally take a ruler and measure it, and I'm going to get I'm just going to do it really quickly, 6.5 centimeters. So it's going to be 6.5 centimeters minus, and the distance from P1 is about 5.7. So it's 5.7 centimeters. And if we get out a calculator and we just subtract these two numbers, so we take 6.5, subtract 5.7, we get about 0.8 centimeters. Okay? Well, that says it should equal 1/2 of the wavelength. Well, let's go over here and measure this wavelength. The wavelength is about 1.4 centimeters. Divided by 2 is 0.7 centimeters. So 0.8 and 0.7, I mean, these are really small numbers. So they're basically the same value. If I measured it more accurately, because if you see the way I put the P there, I maybe wasn't measuring exactly to that nodal point. So within the error of measurement, we can see that very close, we're going to get this 0.7. They're going to match very, very closely. So we can see that based on the wavelength measurement, the path difference for the first nodal line is in fact 0.7, and therefore it's out of phase by 1/2 of a wavelength. So that's all you have to do. As we go to further ones like P4 and all that kind of stuff, they get out of phase by even more because we can see that the distance they're traveling is much greater than the other one. Works on either side because it's symmetric on both sides. So in your questions on the back, first part is, it says what 3 factors must be constant in order for a stationary interference pattern to happen. You can write those down. There's some other information here. If it ever says something like the smallest corresponding path difference, that's the very first one. So given that there's a nodal point where the two waves overlap, find the smallest corresponding path length difference. So the smallest corresponding path length difference is always just the first nodal line. So it's lambda over 2. So you're literally just having to take the wavelength and divide it by 2 in that case. For the other ones, it's going to give you, for number 3, it says in a ripple tank, a point on the third nodal line is 37 centimeters from a source, from one source, and 42 centimeters from the other source. So clearly there's a difference of 7 centimeters. The sources are this far apart and are vibrating at this frequency. Calculate the wavelength and the speed of the waves. So we can get the wavelength by looking at the fact that this is the third nodal line. So that's P3, n equal to 3. And we're able to find the difference between these two values, and that is going to equal 2/2 of a wavelength. And then you can figure out the wavelength. If you know the wavelength and the frequency, then you can figure out the speed of the waves. The point that the sources are 11.2 centimeters apart isn't necessary in this calculation. And we'll actually see that later on we're going to figure out that there's other ways to calculate the path difference using that separation, that value of d, because we're eventually going to say this works for water waves and waves that we see in everyday life. But can we see this effect with light? If we're trying to show that light is a wave, then somehow this will have to relate to light at some point. So finish up that package with the work that's given to you following this analysis, and good luck with that. Can't turn it off. No, I'm not like, not kidding. What's that?